Scientists often get letters from well-meaning people who think they've made some great scientific discovery. Usually they've discovered that protons are brown, or the theory of relativity is a colossal mistake, or something like that. And given time and patience, we often try to answer those letters and gently tell them that they really haven't changed science forever after all. But you might wonder, what really would constitute a great scientific discovery? What is the sort of thing that would make scientists sit up and take notice? Well, let me give you an example. There are certain fundamental constants of nature. For example, remember there is G, the universal constant of gravity, which is equal to 6.7 times 10 to the minus 8 dyne centimeter squared per gram squared. Or there's the speed of light. The speed of light is equal to 3 times 10 to the 10th centimeters per second. And there's, well, the electric charge on the electron, the fundamental unit of electric charge, which is 4.7 times 10 to the minus 10 in electrostatic units of charge. These quantities, and others like them, completely govern the nature of the world that we live in. If any one of these quantities was different in magnitude from what it is, the world would be completely different from what it is. And yet, we have no idea of why any one of these quantities has the size that it does. But every once in a while, somebody comes along and discovers that two apparently unrelated fundamental constants are really related to each other after all, that the size of one is a result of the size of the other. Whenever that happens, two previously unrelated fields of physics are brought together into the same simple story. And that is always a great discovery. It's a discovery of that kind that I'd like to tell you about today.
Not all physicists are created equal. Only a handful are blessed with the vision of a Kepler or a Faraday. Few will share the Nobel Prize with Albert Einstein. Fewer still the fame or the fate of Galileo. Never again can the universe be seen with the revolutionary view of Copernicus. And there will never be another Isaac Newton. But if the life and work of every notable physicist were displayed in one great hall of physics, the exhibits and demonstrations would soon reveal that all of them have something in common. No matter where or when they live and work, all physicists seem equally fascinated by the mysteries of nature. For example, consider the mysterious nature of light. The very idea of light, and especially the speed of light, have been as hard to comprehend as the unimaginable vastness of the universe. In cosmic terms, the sun, a rather common star, is relatively close. Its light reaches the Earth in a few minutes. But from deeper space, light travels so far that its flight isn't measured in minutes or hours, but in light years. From the Earth, the nearest star beyond the sun is 4 light years away, which means that traveling at 300,000 kilometers per second, it takes the light from that star 4 years to reach the Earth. And for year after year, right here on Earth, the most impossible thing about the speed of light was an accurate way of measuring it. In fact, for the longest time, the speed of light was beyond comprehension. Early scientists saw it as an infinite thing, a phenomenon which travels instantaneously from source to observer. But a few people began to suspect otherwise. In 1675, Olaus Rømer, a Danish astronomer at the Royal Observatory in Paris, observed an apparent delay in the eclipses of Jupiter's satellites and used it to estimate the velocity of light. In 1849, Armand Fizeau used a rotating wheel to measure the speed of light. He measured it both in air and in water. In 1850, another French physicist, Jean Foucault, did much the same. The inventor of the gyroscope, Foucault measured light's velocity with a rotating mirror. These experiments were quite advanced for the time. In fact, no one really did much better until the 20s rolled around, 1926 to be exact. In that year, Professor Albert A. Michelson accurately measured the time it took light to travel between two peaks above Los Angeles, Mount Wilson and Mount San Antonio. The two mountaintops are about 30 kilometers apart. It would take nearly 1/10,000th of a second for light to travel from one peak to the other. And that was long enough for Michelson to measure it with precision.
30 kilometers. About 1/10,000th of a second. Those were Michelson's components in measuring the speed of light. He reported that the speed of light is equal to 299,796 kilometers per second. That is almost exactly 3 times 10 to the 8th meters per second.
Why does the speed of light have that specific value? And why is it a fundamental constant of nature? No one really knows. But in the meantime, scientists have only marginally improved upon Michelson's measurement of a fundamental constant that determines the scale of everything in the universe. The speed of light is one such fundamental constant. And the constant in Newton's law of gravity is another. For that reason alone, Newton might have strutted his entire lifetime as England's greatest scientist. But in the realm of scientific experimentation, Newton was no match for Henry Cavendish, an Englishman who measured the constant of universal gravitation. In the process, Cavendish weighed not only the expanding British Empire, but he actually weighed the entire planet. By any measure, weighing the whole world is quite an accomplishment. However, while all scientists aren't as ambitious as Henry Cavendish, neither are they as modest. Cavendish saw to it that his notebooks were not made public until after his death. In any case, whether one hides one's papers from the world like Cavendish, or shows them off to the world at large like Galileo Galilei, all great physicists seem to keep notebooks. And all those notebooks, no matter the subject or style of eventual publication, seem to be journeys into the world of experimentation.
It has to be copper or it has to be zinc. All right, well, I'll have another go.
At times, a physics laboratory may seem tedious,
You let me know. Yes, of course.
and at times, that's just what it is. Yet this is where the physics of the universe plays on a regular basis. And in that light, an ordinary laboratory can be seen as a magical place. Zipping through space almost as fast as the imagination can picture it. What's more magical than light? More powerful than the raw force of electricity, or more pervasive than the influence of gravity. Electricity and gravity. When physicists have an understanding of those two forces, They approach the scale and structure of the universe. But to complete the journey, they need to make a connection with another force, the phenomenon of magnetism. Magnetism differs from gravity and electricity in a subtle way. Gravity, a force acting between masses, always attracts. Electricity, acting between different charges, also attracts. But acting between charges that are the same will repel. Magnetism, acting between magnetic poles that are different, also attracts. And between magnetic poles that are the same, repels. The subtle difference between magnetism and the other forces is that magnetic poles are never alone. They're always in pairs that are both equal and opposite. In spite of their differences, gravity and electricity obey similar force laws. And so does magnetism. Electricity and magnetism. The connection between these forces was made in the Great Hall of Physics.
Discovering a connection between electricity and magnetism was made in the year 1820 by Hans Christian Ørsted. The legend is that Ørsted made his discovery during a lecture while doing a demonstration by accident. There are some people who don't believe that that's possible because scientific discoveries are not made by accident, and so there's another theory, and the other theory is that he purposely made his discovery during a lecture in front of an audience so that there would be plenty of witnesses and nobody would ever think that he had made it by accident. But in any case, I would like to show you what that demonstration might have been like. So I've set up the apparatus here to do a demonstration for you like the one that Ørsted did that evening. So let's use our imagination. The year is 1820, we're in Copenhagen, it's the evening, and we're going to have a gala public lecture demonstration. You are the cream of Copenhagen society. Ladies in evening gowns, gentlemen in frock coats, and I am Hans Christian Ørsted, a brilliant thinker, but a bumbling, inept experimenter and very nearsighted. Now, I realize that you feel that this is somewhat unrealistic because I'm not nearsighted, but we will use our imagination and do the best that we can. Now, 20 years earlier, in 1800, Alessandro Volta had invented the electric battery, or the voltaic pile. And so for the first time, there was a dependable source of electric current. I have an original voltaic pile made for us by Sears Roebuck right here. Ørsted knew that electric currents caused funny things to happen. For example, it could change chemicals into other chemicals, or a wire carrying an electric current would turn the electricity into heat or even into light. And he was absolutely certain that his electric current would turn also into magnetism. So the idea was this. He would pass an electric current through an electric wire, and he would line up the electric wire perpendicular to a compass needle, as you can see here. And then when he passed the current through the wire, it would become a magnet, and we would know that because the magnet needle would swing around to become parallel to it. Now, I'm going to need an assistant in order to be able to do this demonstration. Do I have a volunteer? Oh, good. Would you please be my assistant? If you'll come right up here, what I need for you to do is to throw the switch, pull it back towards yourself when I tell you to throw it, when the experiment is ready. Okay? So when the assistant throws the switch, an electric current will run through this wire. This wire will turn into a magnet, and we'll know that it turned into a magnet because the compass needle will swing around parallel to the wire. Okay? So he sets everything up, and he holds his wire perpendicular to the needle, and when they see it swing around, they'll be seeing the connection between electricity and magnetism revealed for the first time. This will be one of the great discoveries of the 19th century, a dramatic moment. Are you ready? When I say 3, you can pull the switch down. Ready? 1, 2, 3. And absolutely nothing whatsoever happened. So Ørsted, of course, is disappointed, and he tries other things. He tries to make a kink in his wire and pull the magnet around that way, and various other things like that, and nothing works. The magnet absolutely won't budge. And so, of course, he's very disappointed. He tells his assistant to open the switch. He announces that his experiment is a failure, and he sends his audience home. The audience gets up and starts filing out of the hall, and his assistant, who's very sharp, notices that the battery is not quite dead yet. Now, in these days, only 20 years after the invention of the battery, you didn't waste a little bit of electric charge that was left in a battery. Ørsted had a chance to do one more experiment. And so he thought about it and decided to do the one thing that he hadn't actually tried up to this point, because it made no sense to try it at all. What he was going to do this time is to place his wire so that it was parallel to the magnet needle. Now, of course, this made no sense, because if it's parallel to the needle and becomes a magnet, the needle is already lined up with it, and it won't move anyway. Nevertheless, he's tried everything else. He has nothing else to do. The audience is leaving, and he decides he may as well give it a go. So he holds his wire parallel to the needle, tells his assistant to pull the switch. Ready? 1, 2, 3. And the magnet needle swings around, and Ørsted has discovered electromagnetism. Okay, you can open the switch now. Thank you very much for your help. The reason that Ørsted got such a surprising result was because of the way the magnetic field of an electric current works. If this is a wire carrying an electric current, just like the one that we were just looking at, that's the electric current.
Did it really happen that way? It's hard to tell. No one knows for certain what the audience did or didn't see. And over the years, there have been varying accounts of the incident. But the fact remains, bumbling or not, Ørsted's discovery was a stroke of genius. It electrified the finest scientific minds of the 19th century and set off an intellectual charge that lasted 50 years. But why? A battery, a compass, and a little piece of wire. It wasn't his apparatus. It was his fundamental concept. A concept so powerful that when finally understood, it had the power to link ordinary electricity to the most extraordinary lights in the universe, the stars. The stars are linked to each other by the gravitational force law. To find the gravitational constant and to weigh the world in the process, Henry Cavendish had measured the force between two known masses.
The result of the measurement is the value of g in units that come directly from the force law equation. 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared.
A similar kind of measurement can be used to find the electric constant. Here, an electrostatic generating machine is used to put positive and negative electric charge on two parallel metal plates until the attractive force between them overcomes gravity. From the force between the plates, the force between point charges can be deduced. Again, measuring the force reveals the constant in the force equation, and the units of the constant come directly from the force equation.
The constant is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared.
By now, the procedure for measuring constants in force laws is no mystery. Another force, the force of magnetism, another measurement. Another constant with units from the force law. 3 laws, 3 constants. And yet, the point of Ørsted's great discovery is that magnetism and electricity are not separate. So the magnetic constant should be found from the force between electric currents. When electric current flows through metal bars, The magnetic force between them is enough to pull them together. There are no magnetic poles here. The force is proportional to the two currents, measured in amperes or coulombs per second, and the lengths of the two bars in meters. The result of the measurement of the magnetic constant is 1 times 10 to the minus 7th Newton second squared per Coulomb squared. The importance of these constants was understood by many scientists in the 19th century. But only James Clerk Maxwell, 50 years after Ørsted's discovery, finally understood their significance. The electric force and magnetic force aren't independent fundamental forces of nature. They're related to each other, and therefore the constants must somehow also be related. But how?
The ratio K sub E divided by K sub M would have the units meters squared over second squared. In other words, the square of a speed. But what speed? Its square is 9 times 10 to the 16th meters squared per second squared.
Divide the electric constant by the magnetic constant, and there it is. The speed of light. Maxwell compared two measurements that seemed to have nothing to do with light. But hidden within the forces of electricity and magnetism, he found the speed of light. And that discovery would inspire Maxwell to develop a combined theory that unified the concepts of electricity, magnetism, and light. Without Maxwell's discovery, perceptions of the world would be incredibly different. And so would those of the universe.
I once heard a very distinguished friend of mine give an eloquent argument on behalf of pure scientific research. That is, pure as opposed to applied research, the kind that has some purpose. What he said was this: the great discovery by James Clerk Maxwell led directly and immediately to the invention of the radio, and then to television, and to the whole revolution in long-distance communications that we've seen happen in our world. And all of that happened not because Maxwell was trying to discover a way of communicating better, but because he was fiddling around with the fundamental nature of electricity and magnetism. He said if Maxwell had started out to discover something about how to communicate better over long distances, he wouldn't have been fiddling with electricity and magnetism. He would have been doing experiments with giant megaphones and relay stations or something like that. Well, it's an ingenious argument, and it is correct. But if we look back in history, history sometimes has surprises for us. Because the world's first great revolution in long-distance communications occurred when Maxwell was a young man, and in fact, he was intensely interested in long-distance communications. The telegraph was invented in 1838 by Samuel Morse. And by the 1850s, the world was embarked on a great technological adventure comparable to our going to the moon. It was to lay a telegraph cable all the way across the Atlantic Ocean that would reduce the communication time between New York and London from a matter of weeks to a fraction of a second. And so they did that. They sent the ship reeling out the cable across the Atlantic Ocean, and somewhere in the middle of the ocean, the telegraph wire snapped, and it was all over. Well, young James Clerk Maxwell celebrated that occasion by writing a little verse about it, which I would like to read part of to you. In this little poem, the refrain of the poem is under the sea, under the sea. And of course, Maxwell, being a scientist, wasn't going to write that out every time. So he had a scientific notation, an algebraic notation. He wrote U for under the sea, and 2U for under the sea, under the sea. That's the way the poem is written. Let me just read little bits of it. Under the sea, No little signals are coming to me. Under the
Under the
sea,
sea.
under the sea.
Something has surely gone wrong. And what was the cause of it does not transpire. But something has broken the telegraph wire, or else they've been pulling too strong. Under the sea, so many 100 miles long. How could they spin out such durable stuff? Line, all wiry, elastic and tough, in the salt water so strong. Under the sea, there'll be lots of cables ere long, for they'll spin a new cable and try it again, and settle our bargains of cotton and grain with a line that will never go wrong.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.